what we usually do, right? We do introductions. We still can do introductions, but let's do them pretty quickly because we need to get to a lot of stuff. So first of all, let's just make a very quick announcement. Some of you guys already know, so I was running quantum conversations in partnership with IBM as a community organizer, but as a result of this and partnering with my good friends who basically went to IBM Quantum, I was invited to join it. And so basically as of Monday, my title, I'm an IBMer, and my title is Technical Ecosystem Development Lead for IBM Quantum. So essentially, my job will be to do what I'm doing here, but I think as a focus with IBM customers and partners, and but obviously also inviting kind of companies and partners into the Q network, right? But because this is a community space, and we never wanted to be tilted towards any specific vendor or anything, right? So it's kind of important for me to make sure that this is run not by me personally, right, but by a community of organizers. So Stanford Quantum folks gracefully stepped up and offered to basically help drive it. And so Yosh Ketachu, who is the current event chair, is with us here, and he will help us run the program today. And I hope in the future, Stanford Quantum will basically plan talks, but also we have other community organizers. I don't think Stanford folks are kind of against that, right? I think we can basically accommodate a set of organizers, right? So I think I'd like Stanford Quantum folks to be kind of the point of coordination, right? But I'm not going away. I'm going to be helping with this, right? It's just I shouldn't be driving this by myself, right? So which was always kind of not the case, but I just want to make sure that folks understand, right? This is a community group. It has support from IBM, from Stanford, from others, but it's not beholden to any of this. And for instance, I want to be able always to say here, like, Google is better than IBM in this regard. Microsoft is doing something cool, right? And so, Q# has something interesting. I don't think we should be like in this specific space. You're right, there shouldn't be constraints. If you want to help organize it, please reach out. I'll help basically, Yash and Mert, who is the emeritus chair, event chair, who also, he offered to help run it, right? So I think we really have a good group. So that's kind of my announcement. Now let's see, we have about 20 people. Let's do a very quick, I would say at this point, let's try to do like 20-second intro. So just introduce say your name, where you're from, where you're connecting from, and what's your relationship to quantum computing. Let's start with you, Brett.
My name is Brett Koonce. I'm from Missouri in the United States. And I'm just interested in this field in general. I think this is very early days, but potentially wide-reaching ramifications of all this. So,
thank you, Brett. Yosh, you're next.
Hi everyone, my name is Yosh. I'm from Denver, Colorado, but currently I'm living in California on campus at Stanford. And yeah, I'm just really intrigued by quantum computing, quantum information science, and complexity theory, and it's like a potential profession trajectory.
Thank you. Brent Lunsford.
Yeah, so I'm calling in from Austin, Texas. I spent 7 years of my career in Silicon Valley working for a Stanford startup, Silicon Light Machines. I'm currently the global chapter chairman of the IEEE Sensors Council and founding officer of the IEEE San Francisco Bay Area MEMS and Sensors Council. I've had a motto since 1999. It's all about quantum. So thank you for hosting this.
Fantastic. Welcome, Brent. Nick Braun.
Hi, my name is Nick Braun. I've been at IBM Quantum for a long time doing experimental concerns. I'm coming at you from San Juan, Puerto Rico.
Nice. Great to have you back, Nick. Paul Lipman.
Yeah, hi. I'm from the Bay Area, accent notwithstanding. I'm a cybersecurity guy. I'm CEO of a cyber security company, but looking at potentially investing in or joining a startup in the quantum computing field.
Awesome. Welcome, Paul. Adam Glickman. Going once, going twice.
Hello.
Hello.
I don't know if you can see me or not.
We can.
Okay, well, sorry. Uh-oh. Maybe that just did it. I am a local technologist to Stanford area, and I've recently completed the 5 course at MITx online with Understanding Quantum. And my background's been in VenSense and MEMS chips and packaging and quality systems, ISO 9000 quality systems, and been pretty deep into medical and also aerospace.
Great. Welcome.
Bay Area is a fun place to learn new things, and it's
Where the
dynamic.
hub is.
Thank you. Thanks for hosting this.
Sure. Cheryl Filkes of Filkes.
Hi, you got it right.
All right.
I'm an IBM systems engineer in the Poughkeepsie office, and I'm working on OpenShift integration on a number of multi-arch systems, and we've been working on Z and P systems, and I'd love to extend OpenShift to running containers that have quantum capabilities.
That's fantastic. I can't, wait to meet you internally and talk about it. So
Okay.
welcome.
I'll look you up on Blue Pages.
I am already. I am all set
Okay.
up. Actually, I'm going through like days. It's days and days of HR work. I didn't even know that's possible, but it is.
Oh, so, onboarding takes a month.
Thank you. Siddharth Duthaluru. Siddharth. Introduce yourself.
Hi, can you hear me?
Yeah, I can hear you.
Yeah, I'm a student. I'm at Berkeley right now. I'm just here because I got the link and I'm interested. So that's all.
Very cool. That's a perfectly good reason to join us. Welcome. Jamie Gill.
All right, hey everybody. Yeah, so I'm based out of Wisconsin, currently applying for graduate schools in quantum computing. And while I'm doing that, I decided to take a couple of classes this quarter at Stanford University online.
Very cool. Welcome back. Jean-Paul Sadia.
Hello, I'm a student of mathematics. I'm an undergrad student at a county college over in New Jersey. So I'm in New Jersey right now. And self-studying numerical analysis and quantum computing, computational complexity.
Very cool. Welcome. I have a train going by, so please do not be alarmed by loud noises. Jeremiah Coleman.
Great. Hey, everyone. I'm a senior at Stanford University studying engineering physics and economics. I'm the president of the Stanford Quantum Computing Association. I'm interested in quantum hardware in general, going to pursue a PhD in like physics or applied physics. Excited for the talk.
Thank you, Jeremiah, and thanks again for helping us partner Stanford Quantum. That's really good, and that's a good way to start the year. So, thanks. Ion Candelaria.
Hi, yeah, my name is John, and I work at Stanford University. I'm the executive director for the System X Affiliates Program, which is a program where companies from around the world and in many different industry sectors fund research at Stanford. And one of the areas that that we have funded is in this quantum area. So I'm doing the best I can to keep up with what the latest information and news is.
Good to have you back, John. Kunal Ghosh.
Yeah, hope I am visible. Okay, I'm Kunal Ghosh. I'm a business student at Stanford Graduate School of Business. I'm currently in Stanford, California. I'm originally from Singapore. And my background is I was Chief Technology Officer in Laminar Aviation, used to develop optimization-based software, ERP software for airlines. And I have a background of delivering software to more than 40 plus airlines.
Awesome, it's great to have you. Matteo Messi.
Hey everyone, I'm a junior at Stanford studying engineering physics. I'm interested in the applications of quantum physics. That's why I'm here.
Welcome, Matteo. Mert Khan.
Hi everyone, welcome to the first Quantum Conversations of the year. I'm Mert, I just graduated from Stanford. I'm originally from Turkey, Istanbul. Currently I'm located in New York City. I used to lead the partnerships of Stanford Quantum Computing Association, but I really like this community, so I offered to help Alexi with hosting Quantum Conversations. And yeah, and this is my housemate, Santi, who's also very interested in quantum computing. So he's like joining locally with me.
Hi, everyone.
Welcome, Santi. Welcome, Mert, and thanks again for helping drive it. So, I think in the future we'll kind of use Mert as a point of contact if Mert, you're okay with that. So because we need to we need to like you and Josh probably, right, and Jeremiah. So, if folks want to be like organizers, I guess, email me and I connect you with Mert and Josh, and we can get this thing going, right? Like I think the idea is that let's get a group of people, right, and Mert volunteer to drive us and lead us. And I think it's really great because Mert has been in academia now, he's been in industry. It's really good to have somebody who is experienced with, a lot of these things. So that's really great. Thank you, Mert. And, looking forward to a good year doing these things. And Santi, welcome too.
Thank you.
Olive Roerich.
Hi, my name is Olive. I'm a global studies major, but I just independently researched this and I learn more.
I think your connection was a little bit flaky, but we got the idea. Welcome. Let's see. Did I forget anybody? I think Sicheng Zhang.
Hi, my name is Sicheng, and I'm a CS master's student at Stanford. I don't know much about quantum computing, so I'm just here to learn.
Awesome, like the rest of us. Welcome. Let's learn together. And Vasily Nechayev, last but not least.
Yeah, hello guys. I'm a software engineer at Crunchbase, and I'm just interested in quantum computing and wanted to see what progress is being made in this field. So, hello everyone.
All right. And I think we got, I don't know if we got Veselin, right?
Yes, my name is actually Veselin Georgiev. I am in California. I'm regular participant in the Conversations by the Bay. Thank you for Alex for organizing it. I'm also teaching quantum computing for European University and mentoring for the Quantum Open Source Foundation. And just a quick plug, we just started a new cohort number 3, collecting applications for the Quantum Open Source Foundation. So you can take look at the application. I just shared the link.
Thank you. Yes, that's in the chat, guys. If you want to check out Veselin's links, it's great to have you. All right, I think that's all we got for now. So let me introduce our first speaker. And in case you guys join later, we have a bit of change of plan. So we have Brett present AWS quantum talk first. And instead of the panel, we'll have one of the panelists, Mark, do a talk actually instead. And so that will be about sensing, right? So it's a little bit of a change of plans, but we will have still time to have a general discussion, and I think the general discussion topic will still be, how can we make impact with quantum computing this year, because it sounds like a breakout year, right? But let's first go into our program. So Brett Koonce is our first speaker. So Brett presented at my conference, Scale by the Bay, because I used to run and still run a conference in the Bay Area on classical computing, but we also already started having quantum talks there. And so Brett is a really great engineer he presented on Swift for TensorFlow, right? And I think it was a really kind of good review of real advanced technology for software engineers, which is the topic of my kind of traditional community, right? Because if we do with this, if we do computing at scale, we need to, like any other area, progress from kind of graduate student code to production code. And so we're at the point where we need to integrate with a bunch of systems run in production. And obviously AWS is one of the top platforms for kind of scalable global computing. And so it's very interesting to learn what they offer, and Brett took initiative and mastered that. And so he's going to share it with us. It's great to have you, Brett. Thanks to our global communication coming from Missouri. Welcome, and take it away. All floor is yours.
All right. Yeah, thank you again, Alexei, for having me. And then, yeah, say thank you to everybody else for showing up and listening.
In terms of Q&As, what we usually do, Brett, we are supposed to type the questions in the chat, and you can see them there. And so you can pick the questions you want to answer right away, or you can wait, and you can at any point invite people to just say their question on via voice as usual, right? So it's really up to you how you want to drive it. So feel free to pick questions whenever you want, and folks, feel free to type questions in the chat. And
Yeah,
obviously after the end we can have a Q&A.
Yeah, just let me do my flow, so to speak, and then we can do some questions at the end if you all like. So yeah, thank you all for coming. And yeah, today we're going to talk about quantum computing in general, and then AWS braket a little bit in particular. At a high level, the purpose of my presentation is just sort of to try and give you sort of a bird's eye view of this field, sort of an overview of how exactly it works and some different approaches that are out there right now. So towards that end, we'll sort of try to do a very brief overview of the theory behind quantum computing. From there, then we'll look at the actual sort of hardware and virtual hardware devices that are available to run quantum simulations. And then as well, we'll sort of look at some of the software that exists that you actually use to sort of program these circuits and run things. From there, we'll look at sort of just some applications of these techniques, just different fields that I think these quantum computing methodologies can be applied to. And then at the end, we'll talk briefly about sort of this concept of quantum supremacy and the future of this field in general. So the basis of quantum computing is quantum mechanics. I did a talk on this a little over a year and a half ago at TensorFlow World, and I'll simply repeat what I said there, which is that I would love to throw up one slide and you understand this perfectly, but I don't think that's possible. But the basis of quantum mechanics, we'll say, is this thing that's called the Schrödinger equation. It can be read quite simply as simply being E psi equals H psi. The E, you know already, it's the E from E equals mc squared. Einstein's equation, it just means energy. Psi is a little bit tricky to explain, but we might think of it as simply being sort of our system. And then the H with a little hat on it is called H bar. This is just a special form of a matrix called a Hamiltonian. And so Hamiltonians are a way of sort of encoding state, we'll say. So the Schrödinger equation at a high level says nothing more that the energy of the system is equal to the state of the system. This is quite frankly deceptively simple, because a number of interesting observations follow out of this little bitty mathematical equation. And as a result, it's considered to be the pinnacle of 20th century physics. Wave functions are an important part of how all this works. They come to us by way of classical mechanics, where they're used there to describe things like sound, sort of interactions of energy in systems. But the way that quantum mechanics uses them is slightly different. And so I think it bears looking at that as well. In quantum mechanics, we have sort of, we'll say the state, the wave function itself, but then we also have sort of this concept of the conjugate pair, sort of the opposite of the state. And I think this is really kind of where a lot of the mind-bendy stuff out of quantum mechanics comes, because this conjugate literally encapsulates, we'll say, all the other possibilities in the universe. And this is where you kind of get into this sort of like psychological questions and things like that. There's a few different ways of working with these wave functions. A gentleman named Dirac popularized what's called bra and ket notation, where we sort of think of the Hamiltonian as being sort of a projection inner product space of these two vectors. So sort of the one wave function is going one way, and the one going the other way is the sort of opposite or whatever, so to speak. And then from there, we can sort of work with these operators in a sort of linear fashion. So loosely, we might say that the Hamiltonian then is just some real matrix sort of times the sort of the cross product of these two vectors. Like I said, this is a pretty dense field. I saw that you all were talking about the best way to pick it up. I don't know that I can necessarily tell you the right way to learn, but I thought maybe I could talk about some of the stuff that I studied and I found useful, and maybe that will be of value to you. The single best reference I found on the subject of quantum mechanics is this set of online lectures. It's called Quantum Physics 130 from the University of California, San Diego. They literally start with first principles, we'll say, and walk you all the way up to deriving the Dirac equation for the hydrogen atom analytically, which is literally as far as you can do things using analysis. I think you'll find, or at least I definitely found, that whenever I tried to do all this, that I had a lot of holes in my mathematical education. And so I had to spend a lot of time just sort of going back and relearning just sort of my my mathematical basis for stuff before I could actually sort of make sense of all this other stuff. So towards that end, you know, ideally you could take sort of, say, a course on linear algebra or something like that. But for me, I don't like whenever people say, you know, if you want to learn this first subject, you need to go learn another subject and then come back. And so for me, the way I think the best way to do it is sort of just to try and get a high level understanding of the problem, you know, as simple of a high level understanding of the problem as possible. And then you can sort of add more and more mathematical rigor as desired. So towards that end, this book called Quantum Mechanics in Simple Matrix Form by a gentleman named Thomas Jordan is as succinct and concise and clear overview of the subject of quantum mechanics as I have found. He does everything just in matrix forms. He doesn't even use wave functions. And then he does everything else with just sort of like trigonometric identities. So I think literally somebody would say even just a high school understanding of mathematics and a little bit of how to multiply matrices could read this book and sort of understand the sort of high level math that's going on. Professor Jordan has another book entitled Linear Operators for Quantum Mechanics, which is just a really succinct high level overview of this field if you're sort of interested in linear operator theory. And so I would recommend that as well. And then in the process, we'll say, of trying to relearn all this mathematics, I sort of went down the rabbit hole of differential geometry, which I just, you know, I kind of wish all physics was taught that way, you know, just with this sort of clean, unified slate, so to speak. And so this book, differential forms of application.
Peter, could you mute yourself? I think you're unmuted and background.
sorry. Yeah, this book, Differential Forms of Applications of Physical Sciences, is just a really, I think it's just a lovely book, sort of to try and explain physics through through differential geometry. In particular, I became interested in the work of David Hessnes, who spent a lot of time trying to unify the worlds of differential geometry and quantum mechanics. And these last two books are just basically an overview of analysis. They're by this gentleman named Alan MacDonald. But part of the reason why I recommend his work is he's sort of a disciple of Hessnes. So I think that's interesting as well. And then, yeah, these first few books I've shown you are like Dover books on mathematics. So for like $10 a pop, you can buy yourself a lifetime's worth of math, we'll say. Quantum computing proper then is simply bringing the sort of the concepts of computer science to this quantum realm. There's a gentleman by the name of Scott Aronson, who's done some interesting work in his field. But he had this set of lecture notes on the archive that I thought was actually a really as concise overview of this subject as possible. This set of lectures, it's like 10 chapters, and it goes wonderfully off in the deep end of quantum black holes and money and some other stuff like that. But I thought chapters 1 and 2 were just a nice, clean overview of these things. Chapter 1 is simply sort of reviewing the mathematics of linear operators for quantum mechanics. And then chapter 2 sort of just breaks down how we sort of bring traditional computer science complexity theory to the quantum realm. The basic idea in computer science is that we have sort of sets of what are called NP complete problems. Basically, an NP complete problem is just a problem that there's no good way to solve, we'll say. And by extension, the only way to solve it is to test every single possible answer or option, so to speak. If we would allow to turn a phrase, we might say we have to explore the entire universe of possibilities. I personally, SAT solvers are one area of NP complete problems. And this is something I spent a bit of time on in grad school. So that's kind of my window into this whole world. And with SAT solvers, oftentimes to sort of solve a problem, basically at a high level, you're sort of constructed to say, you know, is this problem valid or not? You know, is this a real problem? And so really if you look at how it actually programmed at the SAT solver level, it's actually just all like a gigantic truth statement. You know, is this statement true or false? But in order to know that, you have to actually solve the problem. And by extension, then you can come back to that thing. The reason I talk about this then is because in quantum computing, we have sort of this concept of oracle functions, where we can sort of consult a quantum oracle, so to speak, and it can sort of give us a probabilistic 1 or 0 as to whether or not it thinks that we have the answer. And so then for certain problems, if we set up our systems correctly, what the quantum computer can do is basically explore all these solutions in sublinear time. You can actually go through all the options at a less than O of n complexity. And so ultimately this opens the door up for a sort of explosion of linear versus exponential complexity, or rather for certain problems, a quantum computer can provably solve them faster than any traditional classical computer. So AWS Braket is a service that AWS finally opened up to the public last fall. But basically, then you can actually run quantum circuits on actual real-world quantum hardware. So you can actually just use these techniques directly. They have a handful of different devices on their platform. We'll sort of walk through them here, but you should be aware of these things. They have this Rigetti device, which has 30 qubits. This is a startup that's been sort of at the forefront of trying to build these quantum computers, and they've been able to make them larger and larger. They have another one. It's just an ion trap device. It's 11 qubits. AWS provides 2 sets of simulators. This first SV1 can emulate up to 34 qubits of state space. And then they recently announced sort of this TN1, which can emulate up to 50 qubits, but your problem has to be structured in a certain way. So it may not be able to solve all sorts of problems. And then also the other devices that AWS will provide you access to are sort of D-Waves quantum annealers. These don't really work with entangled quantum entanglement, but there are some interesting problems that we can run on these devices. The first generation of their hardware had about 2,000 qubits, but then they also recently announced a version 2 or whatever, or version 5 or whatever, but has 5,000, like 5,700 of these qubits to work with. So I tried to make a few different demos for you all, and I kind of ended up making this one just randomly, we'll say, but actually I think this is probably the most important slide I can show you. Literally, I've just constructed some random circuits, we'll say, of various sizes, and then just sort of wrote down how long it took to evaluate each one. So literally, we're going from a little bitty 8-qubit system all the way up to 34 qubits. So this blue line then is really just not really showing us anything more than that as our system gets larger and larger, it takes them more and more time in order to evaluate it, as we would expect. And basically the process is, looks to be like almost like a nice, clean, straight line. The trick though then is hidden over here on the left side of this graph, because this chart is in log units. So each of these little gray lines is 2 orders of magnitude more time to run that particular circuit. So from this, we can see that like my computer can emulate like a 20 qubit system in under a second. But as we go up from there, it just starts to take longer and longer to do these things. By the time we get to 33 qubits, it takes about 40 minutes to run a simulation. I went to 34. This took about 10 hours, but technically it was hitting the memory. So my computer started swapping. I only have 128 gigabytes of RAM on my machine. But you can see simply that as we increase the complexity, the amount of time for the computer to simulate it just starts to grow astronomically. We might imagine another rung up on this thing, up to somewhere around, say, 1 million seconds. So one more rung would say take 10 days to run. And if we went up one more rung from there, we start talking about 3 years of simulation time, and one more rung past that, and all of us will be dead before the program finishes. So the first demo I think you should run on the AWS bracket system is simply a demonstration of what's called a Bell's inequality or Bell's theorem. This is just basically one of the classical proofs of the sort of entanglement phenomena. And basically, rather than doing it theoretically, you can simply sort of empirically derive it. So there's a demo of this running on the Rigetti with the AWS thing, and you can simply fire it up yourself. If we can imagine like, small two qubit systems, entanglement, then we can start to think about building slightly larger ones. And from there, I think we can get into the realm of quantum chemistry. I think this is one of the more interesting short-term or one of the more interesting practical applications of all this stuff. We have this whole world of physical chemistry where we sort of like derive the properties of various materials just based basically off of how their electron fields work together. So we might want to say like simulate hydrogen atoms and then try to measure their energy levels. So there's like classical algorithms in this space, notably like the Hartree-Fock algorithm. But the problem with this then is that like Hartree-Fock can't really capture properly a quantum system. And so then you start introducing sort of these adjustments and whatnot in order to, notably like density functional theory, to try and make your predictions match the real world. But if we have a quantum system, basically effectively, we can just simply measure the energy of our quantum system and by extension sort of just derive our data empirically rather than having to do the math behind it. So there's this company called Penny Lane that's sort of a startup in this space. They have a whole website. They have a whole lovely set of demos and sort of tutorials on various different concepts in quantum computing. And I think you owe it to yourself to sort of look through those things. But the demo in particular I would tell you to run is just simply their demonstration of VQE algorithm on H2. That would be the quickest way to sort of wrap your head around this stuff. Yeah, and then, and then they sort of have tools to bridge out to PyTorch, which is a machine learning framework. And so if you have the skills of PyTorch, this can kind of complement some of that. This VQE algorithm, or variational quantum eigensolver, as it's called, I think is just really interesting because of the ability in the near term to sort of run these quantum circuits and be able to do meaningful science on top. So what we're seeing here on the left is just sort of how the VQE algorithm was sort of laid out, how it actually models a circuit for this paper, which came out last year. And then what we're seeing on the right is just sort of the results, sort of measuring the actual electron density, and by extension, the energy levels. To me, the most important part of this graph then is simply the difference between sort of this dark red and this light red line. What it's showing is that basically as they made the system bigger, it was able to produce better and more accurate results. And so by extension, I think in the future, as we can build larger and larger these quantum circuits, sort of using them to sort of run these simulations to sort of match expectations from the last century or so of traditional science in this field, it gives us this really interesting ability to have sort of this feedback loop of sort of reutilizing prior knowledge to build larger and larger systems and circuits. The next demo I think you should run is what's called Grover's algorithm. This picture is sort of attempting to explain how the circuits are laid out for this. There's a demo of this for the AWS system running on the ion trap device. And so you can get it running yourself pretty easily. The key thing to take away from this slide is simply right down here, the part where it says repeat O of the square root n times. This would be an NP complete problem in traditional computing, but this quantum circuit here is able to have an exponential speed up and solve it in sub n time. And so by extension, this opens the whole door to this whole realm of these sort of potentially quantum speedups for these sort of problems. I think the other thing you'll notice if you run this demo is that these devices are quite noisy, and it's going to be a long time before we're, say, cracking encryption systems or anything like that. So from there, I thought it would be interesting to sort of start to look at some of the D-Wave systems, because I think what they do is much more practical for sort of solving problems in the here and now. The D-Wave systems are constructed around what's called this QUBO, quantum, I have the acronym on another slide here, or Ising model. But basically we sort of take our problem, we sort of encode it as a graph, we'll say, and then we sort of reduce the energy of the system. And then in theory, at some point we can find sort of an embedding of the graph that correlates with the answer that we're looking for. So this paper I took these slides from was sort of taking various SAT solvers and then converting them to run on the D-Wave device. And then basically they were talking about a lot of the interesting real world sort of numerical stability and things like that that you had to do and actually get these things to work. And so then this is another paper that was on the D-Wave that I thought was interesting. But effectively what they used the D-Wave device to factor a large number, something on the order of 200,000, which is larger than any other quantum device to date, or whenever this paper come out. But basically they use a sort of some abstract math to sort of convert their factoring problem into a very complicated sort of graph reduction sort of thing. And then this picture is simply just sort of showing how the adjacency matrix and by extension what the D-Wave system, sort of the activations of the system whenever it's actually sort of run. And so then the D-Wave has all these sort of like optimization algorithms that they have that you can run on top. There's a bunch of these sort of acronyms in this space. We have sort of QALO, QUBO, that was quadratic unconstrained binary optimization. And then they have various, basically we'll say statistical optimization approaches. The one that stood out to me then was simply just the traveling salesman problem. In grad school, we had to write a solver for this using simulated annealing. And so this just was very much similar to stuff that I had done before. But basically they sort of model a set of cities, you convert it into a graph problem, and then you can sort of run it on this D-Wave device. So that would be the one I would suggest that you do in order to sort of wrap your head around this whole thing works. Broadly then, the D-Wave, they have a bunch of sort of graph problems and stuff like that. If you're familiar with that literature, that basically you can run on this device and bring over if you have a problem that sort of fits in that realm already. And then, yeah, I thought also I'd mention this other paper. This is from IBM, but it was simply an overview of various different, they basically tried to implement every algorithm they could find on a quantum device. I just thought this was a really interesting paper for sort of showing you a whole bunch of different potential approaches, and maybe you'll find one in there that's of interest to you. And then, yeah, a lot of my background is around neural networks. And so if we have graphs, then we can have neural networks, we'll say. So this is a paper, Convolutional Networks, where they're sort of constructing something like a CNN, we'll say, but in the quantum realm. But they sort of are building these own, their own operators, and then by extension able to sort of attempt to categorize input images as just like a basic sort of neural network layer. And then this was the other sort of paper in that field. It's actually from a little bit before that one, but basically they were sort of just building like basically a quantum convolutional and then a quantum pooling operator. And then they combine these two together to just basically make like a classical fully connected neural network style approach for categorizing in the stitches. So there's a nice demo of this one. TensorFlow has released this TensorFlow quantum package, which is just sort of allowing you to bridge out to the wider world of TensorFlow. And so by extension, you can get data sets and stuff like that for free. And so they have this TensorFlow quantum tool, which is, if you're familiar with TensorFlow, this is just a good set of tutorials and stuff to run through to sort of wrap your head around some of these different concepts. And so here at the end, I'd like to just talk a little bit about sort of this, this idea of quantum supremacy. So this is from the paper that Google published last year, their Sycamore device, which had 53 qubits, and they were able to demonstrate solving a problem that a classical computer wouldn't have been able to do. To me, if we look at this graph, it's basically, we'll say, kind of the opposite of the graph I showed you earlier. But if we look over here, say, at the left side, basically as they're building larger and larger qubit systems, it becomes harder and harder to measure and get the results, you know, to make the system cohere. But they were able to get this 53 qubit system to output the answers that they were looking for. And then over here on the left side of this graph, we're just seeing like sort of estimates of how long it would take for a traditional computer to perform these same results. And then this is a paper that came to us by way of China a couple of months ago. But these Chinese researchers were able to demonstrate what's called Gaussian boson sampling. This is kind of like we'll say a large scale physics experiment where they generate a bunch of photons using lasers. They do some trickery to sort of get them bouncing around together in sync. And then by measuring the results on the other side, they've, in theory, solved a problem that would be impossible to simulate on a traditional computer system. So they claim that their system will do 43, sort of the simulation level is similar to that of a 43 qubit system without much difficulty. And then but they had better and better runs, we'll say. And so they demonstrated that their system had done this experiment at sort of the 76 qubit level as well. So this is the second proof of quantum supremacy, so to speak, that we have now. And so I think, you know, we're seeing the dawn perhaps of this probabilistic processors potentially opening up new doors and new possibilities. And so with that, I thought, you know, I would talk sort of about the frontier, we'll say. This is a slide I stole from AWS presentation last year, but I think it really illustrates these concepts as well. Everything I've shown you today is sort of this zone 1 over here. And with this sort of quantum supremacy experiments, this red dot, we might say that we're starting to cross the, you know, the phase change or whatever into this realm where these quantum computers can do stuff that we've not been able to do yet. And then we can, you know, we can argue about where this orange line should be. Some people think that we can do meaningful, you know, real world problems with, say, like 400, 500 qubit systems. But basically what's cool to me is kind of, you know, we know where we are and we know where we want to be. And just in the future, as long as we can sort of, you know, go down and to the right, someday, hopefully, you know, humanity will be able to use these tools with you know, with some regularity and make them easy to do. So to recap, we sort of talked briefly about the theories of quantum computing, how it works under the hood. We've looked at some different applications that I think will become more and more prevalent in the future. Along the way, I've shown you a set of different demos that you can run to get this stuff working with different various hardware and software approaches in this field. And then finally, I wanted to say that the future is literally people like you and I. AWS, I think it's really cool that Amazon is making these tools basically just available to whomever wants to run them. I think this is just opens up the possibility of, you know, literally anybody in the world being able to play with these tools. And so I think that's just kind of really cool in general. I wanted to say one thank you to AWS. I got some, they gave me some credits to run all this. I want to say thank you to them for that. But all the demos I've shown you today were like $5, we'll say, to run on an actual quantum device. And so by extension, I would argue that we'll say for the price of a pizza, you can, duplicate everything I've shown you here on your own. And so by extension, the only difference for any of you to be a theoretical quantum computer scientist and being an applied quantum computer scientist is a little bit of your time. And so I would hope that you play with these tools yourself as well. With that, I'll say thanks for listening.
Thank you so much, Brad. I see there are some questions in the chat, so feel free to answer these. And meanwhile, guys, you're welcome to ask your questions directly. Are they able to see the question in the chat?
Can I ask a question?
Yeah.
Brett, I'm wondering, you mentioned that for the price of a pizza, you can have fun like that. But I'm wondering how much time do you have to spend actually to prepare on the bracket and get everything in there? I remember when I was applying to get from Rigetti access to their machine a year ago, it was taking a few months until I get into the list and get access to Rigetti, because they give me free access and even credits that I didn't use up. But I'm wondering how long does it take to go through the process with AWS?
Okay. Basically, you can sign up for AWS and then you can load up. They have various notebooks and stuff. It's based around their SageMaker platform. And then basically, you sort of program your experiment into the notebook, we'll say, and then you sort of hit a submit button, and then it sends it out to be scheduled on the actual device. It depends on the device you want. They're not always available, we'll say. But for most of them, we'll say every 24 hours, you should be able to get your experiment in. And then at the end, you sort of get like a batch job back. If you're familiar with sort of doing machine learning workflows with preemptible instances, that's something I do a lot of. And so it's just, to me, very much that same workflow where you sort of, type all your code in there, hit send, and then eventually you get a result back. But yeah, like I said, most of the time, under 12 hours, your experiment will get scheduled. And then, yeah, not all the devices are, the D-Wave ones are usually available. The ion trap usually has less of a waiting time, but then the Rigetti ones seem to be the most popular right now. At least that's what I noticed whenever I played with it.
Okay, thank you.
Other questions?
Hey, Brad. Jesus Christ. All right, we're together. I was just asking on the chat. I'm doing some simulated annealing, and I was wondering if I can use AWS or like Amazon GPUs because it's really slow at the moment. So do you have any recommendations on how to speed up D-Wave simulated annealing through some sort of cloud service?
Yeah, I wouldn't know offhand. I don't know the speed difference between D-Wave services and the Amazon one. Yeah, I don't know that.
May I jump and try to help? I have a kind of question back. Are you trying to run it on the D-Wave, or you're running it in the cloud somewhere or on your laptop?
We're running locally at the moment, but it's constant.
Okay, yeah. So I will suggest then you can get very easily within a few hours probably access to the D-Wave if you go to their webpage and register. And I will suggest just try to run it on their platform because then everything will be perfect there.
On the Leap.
Yeah.
Okay. Okay. Thank you.
Yeah.
Any other questions? All right. If not, then I'll hand it over to Yash, who will continue our program from here. Thank you, Brad, again. Let's thank our speaker.
Thank you all for listening.
Great. All right. One quick second. My computer is glitching right now. Okay, great, perfect. Thank you, Brett, again, for that wonderful talk and quick discussion. So now we're going to be moving on to Mark Kasevich. Mark is a professor of physics and applied physics at Stanford University. His research centers on quantum sensors, precision tests of GR, and advanced microscopy techniques, excuse me. And today, Mark is going to be speaking to us on a talk titled Entanglement Isn't Just for Computation, Frontiers in Quantum Sensing. So thanks, Mark. Take it away.
Cool, it's great to be here. Yeah, so I have a deck of slides that can expand and contract, so depending on time. And I wanted to tell you about some other kind of quantum information relevant topics that I'm involved with. So let me get my slides up here. This should do it. Share. Is that coming through?
Yeah, it looks great.
Okay, and then this is the thing that makes it easier to read. And let's go. Okay, so everybody should see a slide that says the quantum principles of distributed entanglement and superposition. And so I got a couple intro slides here, and then I'll drill into some quantum sensing examples. But I just wanted to start by reminding ourselves of the basic fundamental physical principles that underlie the operation of any quantum 2.0 device. And those are the principles of entanglement, obviously, and also superposition. And I don't really know the sophistication of this audience, but it's based on the past discussion, it seems like you all are up to speed on these ideas. So I just wanted to flash up these cartoons from the EU Quantum Flagship website that came out a few years ago when they were just trying to promote some general understanding of these concepts. And I think this is as good as you can do in a simple cartoon describing these ideas. And the idea with quantum sensing and quantum measurement is metrology, I should say, is that these principles, when appropriately applied to the right kind of sensors, allows you to build sensors that are just better than anything you can do if you're just constrained to using classical principles. By that, I guess I would define it as, you don't have entanglement and superposition as resources. And so then you say, well, okay, you can build better sensors, so what's the point? Because you're always building better sensors. If you're a photonics person, you're always making you're getting better control of optical fields, and that enables you to do better forms of metrology. But there's something that's really pretty significantly at stake when you improve a sensor, and that is that it takes you over a threshold. From being able to observe something that you previously just could never have observed, and it's truly a threshold effect. You have to kind of see it in action to become a believer in this statement. But there's often thought that, well, if I have a bad sensor, I just wait a while and average its output, and then I'll be able to see something. And if I had a better sensor, well, maybe I don't have to average as long to see the same blip. But in fact, the world doesn't work that way. You always have a finite amount of time to make your measurement. There's always some background noise that you have to defeat. And there are a lot of measurement classes where if you just improve your sensor by like a factor of 3 or 4, you go over a threshold from being able to observe something that you couldn't have previously observed. And that observation can be a discovery. I mean, it could be an observation of a gravitational wave. It could be, discovery of dark matter and, the fundamental physics side. It could also be on the technology side, a new form of an observation of a small protein that you just previously couldn't have observed. Now you can observe that small protein and without destroying it, for example, and that can enable like a drug discovery pathway. Okay, so I have a couple of examples that I run you through quickly, and then maybe we can talk or have discussion. Bread and butter in my lab is atom interferometry, and so I want to begin. What we do is we build devices analogous to interferometers for light, and an optical interferometer is beam of light comes in, hits beam splitter. You get two separated paths for the optical fields. They come back together. They because they're waves, they interfere, and the light either goes out one port of the interferometer or the other. An amazing thing is when you do this with single photons, then that interference pattern intensity basically tells you about the probability of a photon clicking in one port versus the other port. And just thinking about those types of experiments really kind of turn you on to the mystery of quantum mechanics. So in my lab, we do this kind of Mach-Zehnder interferometer stuff with atoms. And so on this slide, I show you a false color image. And what you see are two spikes on the left and right-hand sides of the screen. Each spike has about 10 to the 5th atoms. And what I want to claim is each atom that is in these spikes, this is a montage made from a series of pictures in our apparatus. I think I got a picture of the apparatus in a few slides. Each one of the atoms in those spikes is in a coherent superposition of those two spatial locations, separated by 54 centimeters, half a meter. It's the distance between your elbow and the tip of your pinky, for example. Kind of a macroscopic amount. And when I say that it's in superposition, what I mean is the atom is literally in both places at once. And so you say, well, okay, prove it to me. And so the way you prove something like that is you do an experiment where you bring the atoms back together without detecting them, and see if you can observe something like wave-like interference. If you observe wave-like interference after separating them for a half a meter, then bringing them back together, then they sort of had to be in this superposition state. So let's do that experiment. Here's some process data. Again, the false color is proportional to the number of atoms in a given location. And what I'm showing you is interference fringes at the output port of an atom interferometer. And what I mean by that is I've taken those two half meter separated ensembles, brought them back together, overlapped them, and then I actually remarkably observed them to interfere. And you can marvel that nature lets you do this. I think it's just fundamentally amazing that nature will allow such phenomenology. But if you've been thinking quantum computing for a while, that you're no longer that's just a principle that you can engineer with, and it's part of the strange world we live in. So how do we do that in practice? Well, here's an apparatus in the basement of the Varian Physics building. And what we do is at the bottom of the pit on the left, we have a source of ultra cold atoms. We use laser light to refrigerate them, but no cryogens involved. It's just momentum exchange between beams of lasers and clouds of atoms. And if you tune the laser frequencies correctly and intensities correctly, you can't help but to refrigerate the atoms down to microkelvin temperatures where their speeds are measured in centimeters per second, and further cooling methods gets them down to picokelvin temperatures where their speeds are measured in millimeters a second and microns per second. And this is a very different regime from the classical world that we live in, where atoms fly around in the room at kilometers per second. At these low speeds, due to kind of de Broglie's principle, wavelength of the particle is inverse to its momentum, the associated wavelength is large, and hence that allows us to think of the atoms as waves and manipulate them as waves, and it allows them to do the things I showed you on the previous slide. Like when the waves overlap, if the apparatus is properly configured, they'll interfere as waves. The inset on the right, just to give you a feeling for what's going on in the actual Mach-Zehnder interferometer we build. That's the buzzword for the topology we use. The kind of false color indicates the probability of finding the atom at a given position. The yellow arrow shows the distance scale, and we coherently manipulate the atomic wave function using pulses of laser light. And by appropriately designing the pulses of laser light, we can impart momentum to atomic wave packet. Each photon carries momentum hk, h bar k, h bar being Planck's constant, over 2 pi, and k being the propagation vector of the light field, 2 pi over lambda. And that momentum, interplays with the momentum of the atom, mv, non-relativistically. And so if like the atom absorbs a photon, its momentum has to change by conservation of momentum. And just by engineering the quantum process of absorption and stimulated emission, you can make this sort of thing happen with the wave function. And miraculously, after the atom is separated and come back together, you see interference fringes when the thing is appropriately configured. Now let's just think about, physicists love to do these order of magnitude type of thought experiments. How big is an atom? Atoms like half an angstrom to an angstrom. And let's call that half an angstrom, 5 × 10⁻⁻10 meters. 5 × 10⁻11 meters. And how big is a half a meter? Well, it's 0.5 meters. It's a factor of the size of the atom to the separation scale is like 10 orders of magnitude. It's, if you wanted to do an equivalent thought experiment, it's like if the atom is a golf ball, you've sent half the atom to the moon and brought it back, and then you observe interference fringes. Now it's a slightly misleading example because the characteristic scale length for the interference is the de Broglie wavelength, which is much larger than the actual size of an atom, but you get the point. And so part of the technical difficulty in making something like this work is that you have to have it nearly perfectly aligned. It's sort of like building quantum gates. If anything's missing, then that you do not see in the interference. The superposition is not manifest. You just see it looks like two ensembles of atoms that overlap, and they don't interfere. This is why it took 10 years to get this experiment to work. Okay, so what's it good for? What's the disruptive measurement that can be done with such an apparatus? I'll give you a few examples. In the context of the physics department, we're using this apparatus to test Einstein's equivalency principle. And how are we doing that? Well, turns out that here's some interference fringes on the right, and a schematic of what's happening with the atoms on the left as they launch up a tube, and they hit the optical fields that split up and recombine the wave packets, and then they fall back into a detection region, and we see the interference fringes. By the way, the previous fringe I showed you, previous illustration, this one here, I took out the sag due to the acceleration due to gravity, just to show you what's happening with the wave packets. So actually, these things are all doing parabolas under they're free falling due to gravity, as well as separating and recombining. Well, think about the quantum physics of this situation. One wave packet is seeing a different gravitational potential than the other wave packet. All right, and so then you say, well, that means it's got a different gravitational potential energy. And we all know how the phase of a wave packet evolves, potential energy. It picks up a factor of potential divided by Planck's constant times time. And so that's the phase. And so what happens in the gravitational potential is there's a phase shift due to the acceleration due to gravity. And that phase shift is huge. It's like 10 to the 10 radians difference between the two trajectories of the atoms on, say, the lower path of the Mach-Zehnder and the upper path. Now, what does that mean? Well, it means that you can make a very precise measurement of the acceleration due to gravity, like at the part in 10 to the 10 level. G changes by a part in 10 to the 10, and the fringe shifts enough that the atom, instead of coming out of one port of the interferometer, comes out the other port of the interferometer. okay, how much is 10 to the minus 10 of the acceleration due to gravity? Well, the mutual acceleration between two people due to gravity, two people sitting next to each other in an auditorium, is like 10 to the minus 9 g. This apparatus is like sensitive enough to see, like changes in a person's mass at the level of drinking a cup of coffee, and that's as manifest in the acceleration due to gravity. So it's extremely sensitive way of observing acceleration due to gravity. And what we do, we're interested in testing Einstein's equivalence principle, is to ask, do two different isotopes of rubidium, which have different nuclear structure, different mass compositions, do they see gravity in different ways? And what do you mean? What do I mean by different ways? Do they say different gravitational phase shifts? And like the standard theory says, they should see the same phase shift. If Einstein was right, and our concept of GR is correct, the phase shift for rubidium-87, the phase shift for rubidium-85 shouldn't depend on the mass. And so we've just published a paper recently where we showed that at 12 digits with atomic wave packets, that in fact, the Einstein equivalence principle is correct. And the point here is that, one of the things you build a better sensor for is to do some fundamental science. But there's more that can be done. So right now here's a picture from a company which I co-founded called AOSense, where we're building practical sensors based on these interference methods. One thing you might want to do is fly one of these ultra-sensitive gravity instruments in low Earth orbit and measure the gravitational field of the Earth. Why would you do that? Well, because kind of gravitational field that you see in a satellite orbit depends on what's on the surface of the Earth. Like, and there are certain regions where there, for example, it depends on the amount of water that's in the region directly underneath the satellite. And we care a lot about, or I should say geophysicists do, hydrology and measuring the Earth's water table, because as with climate change, the ice caps melt, the water in that has to shift. Where's it going? There's not a lot of good ways of measuring that on a global scale. And so there's tremendous interest in putting up precise gravitational sensors in order to do the simple thing of measuring the height of the Earth's water table globally. And so on the right, there's a false color map where you see regions of more and less, water, and it turns out it's sort of amazing with these geodesy missions. It's possible to, we think, measure water table heights at the millimeter level, which is enough to be really geophysically interesting. And so, heck, just the other day we were on a teleconference with NASA Goddard Space Flight, and we're progressing in along the path to such a mission. And so it'd be kind of cool, if we use quantum interference to actually do something for climate science. There's still, I don't know, we're talking about a flight date of 2025, and that's probably an optimistic estimate. What else? Well, coming to smaller scale instrumentation, it's possible to build really exceptional gyroscopes and gravimeters, things that, like just on the Earth, you say, I want to measure the acceleration due to gravity. Let's not separate the wave packets by 1/2 meter. Let's separate them by millimeters. It turns out you still can make amazing sensors. And so out of AOSense, we're building gyroscopes and gravimeters and other sensors based on this fundamental quantum interference property, which entangles the position of the atom with its internal state. We're building those for applications in navigation and geodesy. And when I say when you build a sensor, certain things that you can and can't do, and when you go over a threshold, well, it's really sort of it's engaging to look at where those thresholds are for various technology applications. And for example, in gyroscopy, the gyroscope is a key element in an inertial navigation system, something that tells you where you are if you don't have GPS. It's kind of amazing what you can do as in terms of being able to navigate without GPS when you have super precise gyroscopes. And I can drill into some of those applications if you're interested in discussing them. And then coming back to the basic science, another thing that I'm doing with my colleague Jason Hogan, Jason is principal investigator on this project, is configuring a very large scale atom interferometer out at Fermilab in Illinois to detect gravitational waves and to look for dark matter. And the principles are similar to what we do when we look for violations of the equivalence principle and so forth. In a nutshell, you're looking for anything with changes the position of the wave packet that either due to gravity or some exotic force or potential, and that change in position is manifest in a shift in the interference fringe. And we think that by building 100-meter scale instruments, we can make some new statements about say dark matter. So that's kind of what I have to say about superposition. And from the point of view of a quantum computation audience, it's what we're doing is single particle with those. It doesn't involve like creating massively entangled states and manipulating them and controlling. It's just these are single atom wave functions, but we control them extremely well. And from a hardware perspective, what a lot of us are seeing, who are my company also is involved in quantum computation hardware and so forth. What a lot of us are seeing is there's a convergence between the engineering that goes into quantum sensing applications and the engineering that goes into quantum computation application for certain types of quantum computation. I mean, I'm all atom based. You need really great gate ops. You need to do rotations almost perfectly, and that's what we need to do when we build those sensors. And it's also what we need to do when we think about networks and so forth. All right, turn the page. Let's now become quantum 2.0 people and say, well, I'd really like to do more than just position internal state entanglement. How can I use entanglement as a resource to improve measurements? And so here what we do is we create massively entangled states. When I say massively entangled, some of the work I'll show you, we're entangling the wave functions of thousands of atoms. And these 1,000 atom entangled states are not controllably entangled in the sense of a quantum register or a lot of quantum registers, but they're entangled in such a way that allows us to do metrology, phase metrology at levels that are beyond anything we can do with single quantum systems. And so the states we make are essentially they're analogous to Fock states, or we sometimes call them squeeze states, depending on how much entanglement we've generated. And the basic method of doing this, if you want a nuts and bolts picture, is we put a bunch of atoms at low temperature in a cavity, and we measure how many atoms are in the cavity. And when we do that, if the atoms are initially in superposition states, then after that measurement, we kind of create an entangled wave function that correlates the internal states of the atoms across the ensemble. Now, there are a lot of details there, but the bottom line is we create this marvelous macroscopic entangled state. And then what we do is we feed it into an interferometer. And that interferometer, in this case, is configured to be an atomic clock. And so if you think about some of the gate operations in an ion trap quantum computer, a lot of times what you're doing is basically building a kind of complicated atomic clock. You do pi/2 rotations, you do free precession, and you do pi/2 rotations. You read out, and what we read out, instead of reading out single qubits, is we read out the number of atoms in a given state across the ensemble. So it's something simpler to do. I don't have to detect individual particles. I can detect ensembles, but I can certainly tell in terms of the performance of the clock, whether I benefit from the entanglement. And so this is a clock engineer's plot that shows the performance of the clock as a function of the amount of time you look at its output. And basically, you like to see these lines be lower on the chart to give you, it shows it's a more accurate clock, more precise clock if that's happening. And you can see the blue is what happens, what you build without entanglement. The black is what happens when you entangle, and you get a substantial improvement in clock performance. And so what we're working on doing now is translating this stuff from laboratory into, atomic clocks that you might find in a data center. And there's lots of reasons to get a better atomic clock. And again, we can talk about why you might want that. The de facto existing technology is this thing from, I don't know if it's called microsemi now. Everybody keeps buying the companies that sells clocks, but that's what it looks like. And what we want to do is bring entanglement to that beast and to improve its performance. And so that's happening out at AOSense, and also a lot of labs, metrology labs across the world are trying to figure out, what the right recipe is to exploit this large scale entanglement for improved time standards and other sensors. Let's see, one interesting thing, I said there's entanglement there, and you say, well, okay, yep, what do you mean by that? And I can talk about the entanglement against a lot of different metrics, like the noise the sensor would have if it wasn't entangled, or the noise the sensor has when it is entangled. One of the interesting metrics is to think about the Bell correlations that exist in the ensemble. This is kind of like measure of two-gate fidelity in quantum gate ops. And so back in 2017, part of my team, went and looked at a measure of the the existence of Bell correlations in these ensembles, and it's stunning how quantum the states we make with this cavity assisted method are. And in fact, we observed a 56 sigma violation of. It's not exactly the Bell inequality. It's the formal words are the Bell witness criteria. That's a formulation of the Bell inequality for macroscopic ensembles. This just shows, and that's what this chart shows, is that's like, this isn't your average classical ensemble of atoms. This thing is highly correlated, and that's what we need to feed into this measurement apparatus to actually improve the precision of a clock. All right, let me give you one last example, and then I'll turn it over to you guys. I just described a couple measurement strategies that were used to kind of look at things that were kind of macroscopic, or can I use similar methods at the nanoscale, building interferometers and so forth, to improve microscopy? And if you in microscopy, and now we're getting kind of far afield from I understand from quantum hardware, but stay with me here. In microscopy, one of the things that you'd really like to do is this is holy grail category, and in my view, and in the view of life scientists, this is as much of a holy grail as building well, maybe not a fault tolerant quantum computer, but building a good piece of quantum hardware that computes. I'd like to be able to look at small stuff without destroying it. And right now I can't do that. You look at the cover of Nature and you see all these fancy electron microscope pictures, most notably recently of the coronavirus, but also of other small proteins. Turns out that when you look at those with electron beams, then that's the only probe we have really to see at the nanoscale. It's impossible to right now image that stuff without absolutely destroying it. The radiation damage from the electron beam is just monumental. And so the question is, can we do some quantum measurement in such a way that doesn't destroy what we're trying to look at? And could we image something at the nanoscale that's alive? We have to just be a little bit philosophical about what we call living, but maybe I shouldn't put it in such metaphysical terms. Could we see a protein fold without destroying it? That kind of thing. And that capability is enabling, for example, for drug discovery. Okay, so what I just described in that previous entanglement example was a quantum non-demolition measurement for atoms. And I applied that non-demolition strategy to an ensemble of atoms to create the entangled state that I use to make the clock. Question being, is there a family of quantum non-demolition measurements that I can also use for imaging small proteins? And speaking in terms of quantum computation here. Is it possible to entangle the state of my probe, the electron, with the state of entangle, with the state of the thing I'm trying to image? And then after I've done that entanglement, then I can use all my quantum engineering tricks to collapse wave functions and so forth to learn in controlled ways about the thing I'm trying to study. And on the right is one of these biophysics, structural biology views of a protein. It's a virus particle. And so we're building. It turns out you can do that. And what the key ingredient is, when I use that cavity to non-destructively detect atoms, what I ended up doing was taking the wave function of a photon and making it pass back and forth through the ensemble of atoms a lot of times. And it turns out that that sort of strategy dramatically leverages the inelastic to elastic scattering ratios in the favor of elastic, which is, if you want to do coherent operations, and you're a hardware person, that's what you're looking to do. And so we want to do the same thing with electrons. We want to make an electron go back and forth through the image target. In this case, is the MAR VP35 protein, which is something from my perspective as a physicist, is something I just download from the protein data bank, and I have no idea what this thing does. But people tell me it's interesting to image that. It's about 5 nanometers across in that image, and I think it's 15 or 20 nanometers long. And if you put this thing in a conventional transmission electron microscope, you just melt it. And kind of if you try and simulate what you could do if you didn't melt it, you just wouldn't have enough electrons going through that thing to see a darn thing. And that's what I kind of show in that on the right-hand side, the picture there. If you build one of these multi-pass quantum non-demolition microscopes and you make the electron go back and forth like dozens of times, it turns out that you can actually build up enough phase shift as the electron wavefront goes through that protein in order, when you make the measurement, collapse wave function and so forth, you can actually see the protein, and in a quantum non-destructive way, which is sort of amazing. It's the only way this can happen is via quantum mechanics. And so right now, my group, we're trying to build one of these microscopes. I can tell you in a year or not whether it's going to work. One more thing to tell you, and then I'll finish. So maybe in your intro quantum course, you were introduced to the idea of a counterfactual measurement. And I know there's some QC schemes that invoke counterfactual, and it's one of these magic and mysterious things in quantum mechanics, in my opinion. So look at this diagram on the left. It's a Mach-Zehnder interferometer. Quantum particle goes in both paths at once, hits a beam splitter at the exit, and depending on the relative phase between the two beams, the detector D1 clicks or the detector D2 clicks. Now, because it's an interferometer, I can align it so that the detector D2 clicks every time, just by adjusting the relative path length. So I do that. And so it's kind of an uninteresting thing. I put particle in the input port and D2 clicks. Now do the following thing. Put an object in one of the arms of that interferometer. Maybe it's a piece of protein and I'm using an electron to do it, and ask what you expect to see happen at the output of that interferometer. Well, now if you think semi-classically, I blocked one of the arms, so I no longer have that interference that made the electron come out and hit detector D2 and have a click every time. If I block one of those arms, what must happen is part of the time D2 clicks, and some of the other times I send an electron through, D1 clicks. Now, if detector D1 clicks, I have to be able to infer that there's something in the interferometer, because if there was nothing, if there's nothing in the interferometer, D2 has to click every time. I put something in there. The only way I can get a click in D1 is something's blocking one of the arms. But the detector clicked. So the electron was not absorbed by the object that was blocking the arms. The electron sailed right through that apparatus, did not, quote, interact with the object, and instead it interacted with the clicking detector D1. So when D1 clicked, I learned non-destructively about the presence of an object in the arm. I observed that object, if you will, non-destructively. So that's a category of quantum non-demolition measurement. And what I just described to you with that multipass microscope is one where we want to change. This is kind of a bad way of doing non-destructive measurement, because some of the times D2 clicks, even when the object's in the arm, and you can't make any solid inferences. But by doing that multipass method, you can get to a situation where you're highly efficient in this counterfactual inference, that when your detector clicks, you know that there had to be something in the case of the microscope, the image plane. Last slide here. So we're trying to do that with electrons, but light also gives us marvelous quantum particles called photons. So can we do something like this with photons? And so we've been building microscopes that are exploiting that same counterfactual principle. And this is the same multipass principle, we call it, where when something in your detection plane clicks, you can make the strict inference, kind of validated by quantum mechanics, that there had to be something in the image plane. And so we're just getting our proof of principles going. On the left, you see some slides where each one of the bright spots on that is when we send a photon in and a single photon detector clicks, and we can infer that there's a small bead in the sample plane. And on the right, just for fun, we put a red blood cell in there, and when we see a click on the right, a single click, we infer with high probability that there had to be a red blood cell in the path. And where we want to go with this, well, we're still trying to figure it out. I think there actually may be quantum compute paradigms involved in this, but it's certainly, I think, also interesting to ask, can we do something more fantastic, by entangling biological systems with quantum particles, and then manipulating and measuring. So that's what I got, and let me just cap. So what I wanted to do is kind of expose you to, if you haven't been exposed to, some of what's going on the metrology side of the quantum 2.0 revolution. And a lot of us, in terms of overall funding, the metrology side is attracting a lot of funding. I mean, in Europe, it's about 40% of the quantum investment. In the US, maybe 30%. And it's not as flashy. You're not going to read about it as much on the cover of the New York Times or The Economist. But the reason why investment is going there is because it's a little bit nearer term, and you build a good enough sensor, and you can do something that you couldn't have done before, which is sort of what we're trying to do with quantum computation and networking also. So that's what I have to say. Thanks for your attention.
Thanks so much, Mark. Great. So I guess I'll open up the floor to any questions anyone has.
Yeah, we got one on the chat. If you can see that, Mark.
Oh, okay. Let me get up the chat here. I haven't been teaching, so I'm not as recently, so I'm not as Zoom enabled as I should be. So let's get.
I can read it if you'd like, also.
Yeah, please do. I'm having trouble getting the.
Yeah.
Okay, is that what I need to do?
Oh, this is from Paul Lipman. Mark, do you think that this neutral atom laser cooling will be more likely path to large-scale quantum computers than the supercooled qubit approach?
Oh, great question. Yeah, and so out of AO sense, we're looking at this. I would say right now it's really hard to predict on the hardware side, and Quantera, which is a company founded by some of my colleagues out in the Boston area. Maybe you guys have heard from them. Vladan Vuletic, Misha Lukin. They're using neutral atom in lattice with Rydberg gate interactions, Rydberg mediated gates. And they're actually doing that system is really amenable to some quantum simulation tasks. And they had some big splash results a couple of years ago, and now if you go to the Quantera website, they're making 2D arrays of atoms and doing kind of, I think, spin glass type quantum simulation work. Where's the bottleneck on neutral atom QC with Rydberg? Well, there's just like with ion trap, you have a spontaneous emission and inelastic interaction in your gate operation that limits the efficiency and fidelity of the gates. But it's at a place where, I think you can do intermediate scale. I don't think you'll get large scale, but arguably nobody knows how to do large scale fault tolerant right now. But at the intermediate scale, hundreds of qubits, the numbers sort of pan out. It's just the frustrating thing is, and why you just don't want to jump in and say, okay, we're going to go all the way on this is, it's not clear that you can extrapolate to a larger number of gate operations. But it's certainly very promising, and it just goes to show you on the hardware side that, if you talk to people 4 years ago and said, well, is anybody going to do a neutral atom lattice QC that's competitive with superconducting or ions or solid, solid state, you wouldn't have said that they had a chance. And then you have a disruptive idea, and then the hardware starts coming along. And so it'll be interesting to see where they go. And there's another company up in Berkeley, Atom Computing, that's doing this with atomic strontium. Quantera is an atomic rubidium. Strontium has some favorable level structures. It maps onto precise atomic clocks. And so a lot of the physics that I talked about with entanglement for improving quantum clocks is what they're exploiting up in atom computing. So I don't know, if I had to bet, I'd put a bet on them. That's
Great talk, Mark. Actually, that's very interesting. This morning, I was just finishing my teaching with explaining the Elzer Vladimir bomb tests to students. And it's kind of realized that it's really cool if there could be practical upcoming tests or validation experimental to really show how the theory is matched with experiments. Do you know anyone trying to build some kind of equivalent process or something?
Yeah, for sure. There are some, let's see, there's some, if you go into the literature on that, there are some foundational experiments done in the early 90s with photons that, kind of are considered like the experimental demonstration. For the high efficiency bomb testers, the ones that, are a little bit more than Mach Zenders, I was involved in one of the early experiments in the 90s with photons. And just recently, in fact, just this afternoon, I received a paper for review that talks about doing this kind of thing with electrons. So, it's those demonstrations are out there. In terms of having real impact, I don't think there's yet been a device on the measurement side that takes us beyond just like, this is a quantum curiosity. but I'm optimistic that's going to happen, primarily because of some of these biological applications where in transition electron microscopy, you have, when you look at and you build up these maps of small molecules, you have hundreds of thousands of identical copies of the system you're looking at. And so if you have a mechanism to know, when you're probing a system that, the time you probed it, it was a non-destructive probe, then for those systems that, you learn that about, you'll actually have a damage-free inference. A lot of the other samples will be just, the bomb will explode, but as long as you can detect that, if you can hear the bomb going off, you just choose not to look at that, you post-select. So I think we're going to see microscopies evolving in this direction. Time will tell. Yeah, it's fun. It's fun to teach that, though, isn't it?
The thing is that in quantum physics, that's one of the Achilles' heel, that once you look at something, you change its state. And if you want to maintain that you're continuing to operate on unchanged state, then you have to actually focus on this kind of non-destructive interactions.
Right.
Yeah. Thank you.
Yeah, thanks. Thanks.
Hi, Mark. Oh,
Can
sorry.
I ask a question? Can you detect neutrinos?
Could we detect neutrinos? There are, so speaking broadly and maybe not as much in quantum measurement, language, there are proposals for neutrino detections with ensembles of atoms, and it's up at Triumph. There's a group that's kind of focused on that. I don't think the numbers are really competitive, so there's no large scale investment in that, but yeah, it's certainly been discussed, and it's sort of an indirect path, and I'm sort of forgetting some of the details, but I know there's a group at Triumph up in Vancouver that's looking at that.
The reason I ask is because there's tomographic methods that have been. There's a theory that you could map the Earth's interior with neutrinos. Because
yeah.
Yeah. I'm interested in
really cool
tomography.
Stuff. Yeah, probably it's better to use a conventional detector to start. But and it's interesting. If you have a really great neutrino detector, you can let your imagination run wild in terms of applications. And I've been in some environments on the national security side where maybe people have let their imaginations run a little bit too wild. but mapping.
I'm not that guy.
Okay. Yeah, Earth mapping is really it's a cool application.
Yeah. That's the reason I asked. Thanks.
Yeah, you're welcome.
Hi, Mark. Back on the photonic side, I was wondering, like, PsiQuantum claims that in the next 4 years they're going to have 1 million qubits. So with photonic quantum computing. So do you think that statement is believable? Like, to what extent?
Oh, it's for sure believable. They have the capability of doing the large scale photonic integration, and that technology is there in the foundries. But as we've learned, it's not just your qubit count, and so you can put down 1 million qubits, and that's their sell, is that they have a way of getting to the the fault tolerant, error corrected thresholds and qubit count that you need, but a lot of people are wondering whether they can get the fidelity to where it needs to be, and also the detection error rates and so forth. I mean, you need to have that. The photon comes in, that detector needs to go click, and if it misses one, then that's just going to make your compute cycle more inefficient. And so even though you had all those qubits, you can't use it. So stabilizing the interferometric pathways between 1 million qubits. I don't think I think even the PsiQuantum guys would have to say that, they're just going to get into a regime that they're going to have to go into learning mode, because these multi-photon entangled states, we can predict that they're super fragile, and so it's a question of, after you lay down all those gates, whether you can actually use them to do something. And what I find really exciting about PsiQuantum technology is there's a lot of one message that I've had in my involvement of pushing quantum technologies is when you do that, you're perfecting classical technologies. And so there may be other sensing or compute paradigms based on classical fields that might also advance. And so I think it's going to be really cool to see where the PsiQuantum stuff goes in the coming 5 years. And it's a very impressive effort. I think it's I should have mentioned them in when I was just rattling off a list of compute options, because I think they're one of the dark horses out there. And they don't consider themselves a dark horse; they consider themselves a front runner. But right now, everybody, you said, well, what's the most likely? I think most people would say, oh, it's going to be the superconducting qubits. And I think when you take a sober analysis of where superconducting is and where it can go and where optical is, and photonic gates, you start to be enthusiastic about photons. So.
Great, thank you.
Mm-hmm.
All right, guys. Well, thank you very much again, Mark, for the great talk, and thank you, Stanford Quantum, for taking charge. I guess we had a very good start of the year, a very good turnout. Thanks everybody who stayed with us almost 2 hours. So for the next talk, we are pretty open, right? We are doing kind of once a month. So between me, Mert, Josh, and maybe some other folks who want to organize, we'll get together. We'll come up with a plan and we email everybody because everybody had to register, so we'll have the email. So we'll email you guys the update, and we're looking forward to really making it a fun destination. So if you want to give a talk, please reach out to any of us. I think we'll basically make it fun. Thank you, guys.
Yeah, thank you, everyone.
Thanks, everyone.
Yeah, hey, thank you. Enjoy.
Thank you all.
Thank you. Thanks again, Mark and Brad. It was excellent. Thanks for starting this year on a great note. So looking to learn more from you guys.
Okay, take care.
Thank you.
Bye.
Bye.
Bye.